So the next speaker will be Francois van Heerden, and he will be presenting on the magic of color.
Hello everybody, my name is Francois and I'm going to present my talk today on color. Just a little bit about me before we get into the talk. I'm originally from a research psychology background of all places. I finished up my master's in research psych a couple of years ago, and since then I've actually been working in market research. I've been with Cantor now for a couple of years, and we actually look after quite a bit of customer data, brand data, and we specifically focus on forecasting, choice models, predictions, segmentations, and a whole other set of techniques. But you can ask me more about that afterwards. But back to the talk. So why color? If you think about color, we actually really need to pay more attention to it, because everything that we finally do, the outputs will contain some sort of a color element, even these maps that you saw from the first talk. So color is always very relevant to our visualizations. And they in fact do require some creativity. So really the combination of good data, the right chart type, and color actually together really creates the best result for us finally. And we really need to create that to emphasize our information in the best way. I think if you've all looked at Tidy Tuesday, as some of you know, the visualizations are amazing, and often that is actually attributed to the color that is used and the technique that's used to visualize that data. Now, just to show, I don't think it's necessary to show, but we've all seen these really ugly charts in publications, and we can definitely do with less of that and far more of this. What I really like about this visualization is that the lighter blocks are actually representing their success rate, their overall grants that they've requested, and the darker blocks are actually indicating their success rate, and then you have this nice coefficient at the top showing you the proportions, and you can very clearly see how the color is actually helping the elements. Okay, sure, sorry. All right, so I know some of you might feel, what is the point of colors? Let's just choose the right colors and be done with it. And to that I would say that actually to choose colors that are visually appealing is quite easy and it seems intuitive, but if you have like a very big color task, it becomes actually slightly more difficult to do. So if you have to do like a big color task, are you going to use a package? Are you going to randomly choose colors? Are you going to choose them painfully by hand? So for my pet project that I've been working on, I needed about 200 different color palettes. And I knew that for what we have available, nothing was really going to cut it. Color Brew is an amazing package, but for most of the purposes for this, it just won't cut it. So I thought of getting some training data, uploading it, drawing some palettes, and taking it from there, sort of. So sources of data for this. I actually decided to use color flags as my input, just given how rich color flags are and what they can do and the type of features that they have. So, case in point to the conference, I think it's quite appropriate. And yeah, sort of the visualizations that I finally want to get to is this. So there's a very small map of Joburg in its color elements. I've produced some of these at about 25,000 pixels in width and height with color elements. What has really been helping me with getting onto this project was actually what was available, and Twitter actually helped quite a lot. So I was able to ask people, where can I get flags in a repository, and people quickly pointed me to Shiny Flags, and I got flags as my input data. So in terms of the actual data, Shiny Flags has about 256 flags. Unfortunately, the package is not published on CRAN just yet, but that was more than enough to get me going. These flags are saved in SVG, so they're scalable vector graphics, and they're not really good for my purposes, as I kind of want to analyze them on a pixel level. And SVGs, as some of you would know, are actually shapes, numbers, and coordinates, and not actually a pixel grid. So after converting them, I ended up with my flags in 640 by 480. Just before we kind of get into how I then got my palettes, just a little bit about the composition of an image. You can think of each pixel actually being represented by a cube, and we actually have 3 dimensions to this cube, RGB, as probably many of you have known. You can also think that we have about 16.7 million possible combinations or positions within this cube representing each pixel. So if you think about our image, we actually have a width and a height, That's basically our one plane, and then we have a red, a green, and a blue dimension following suit that has a corresponding value to each one of those pixels. So in terms of libraries, what are actually available? So the first two packages that I looked at was PaletteR and ImagePalR, and both of them were actually making use of k-means to derive these colors. There's one other interesting package that I found at the end of my journey that I'll also show you at the end. All right, so how's PaletteR actually doing it? Quite simply, they're just specifying a picture, they're converting it into a three-dimensional RGB matrix, they're applying k-means, and then they're moving to the HSV color space to remove too bright and too dark colors, and then further getting the most distinct colors within that, so to speak, cone space. I won't be focusing too much on HSV, but that's also just something to be aware of when you're working with color, that finally you do want to look into that space with what you're working with. All right, now the real crux of it is that it's actually using k-means, and k-means, like some of you have known, is an unsupervised learning method. And it's a clustering technique. We're actually trying to see if there are underlying subgroups or different clusters within our data. Now, k-means is trying to partition our data into a k number of groups that are completely non-distinct. So all points need to be part of a single cluster, and they can't be part of two or more clusters. So for k-means to find the best solution, it's actually trying to do two things simultaneously. It's trying to maximize the distance between clusters as far as possible, while it's also trying to minimize the distance of points within a cluster. So since it's trying to find a solution, it has to go through some sort of iteration or convergence process. So often, as you'll see, that we'll either converge to a solution or we'll get to a point where we've gone through our maximum iteration count. And then almost as a caveat as well, with k-means, often more than one good solution exists, and you can end up with multiple good solutions. So let's actually just illustrate it. So let's say we have three clusters that we want to find from this data. You'll see that on iteration 1, we actually start with three randomly selected points as our centroids. And then from there on out, we compute the sum of square distances between those points and the centroids. And then we compute our new centroids after we've allocated our points to our initial centroids, and then we then pick new centroids based on all the points attributed to that cluster. From here on out, our step 3 to 5 actually just repeats. Let me just get rid of that. From here on out, we actually then just repeat steps 3 to 5 until we get to a point of the centroids actually not changing, or to the point where we've reached our max iteration count. So how is this actually looking in terms of the PaletteR code? So you'll see that the create palette function is just reading it in there, highlighted in blue, and then from there we're actually creating our matrix after we've looked up the initial dimensions of the colors of the pixel. From here on out, we have the optimized palette true. So in this instance, it's actually applying k-means first and then looking at the HSV color space. But for our purposes, let's look at the else section. So it's actually, like you can see, just using k-means, we have a maximum iteration count of 30. And then we're actually returning our centroids as our initial palette values. And then we're just applying RGB function onto it to actually extract those colors in its X codes. All right, so let's get into a couple of examples. So I wanted to use this Antigua and Barbuda flag. I have a couple of others that I also use to kind of work my way through. I chose this one specifically because it actually has a lot of interesting features to it. But as you'll see now, something becomes very evident when you start running k-means on this flag. So I think it's already very clear that we end up with this odd brown in our flag. And there we get a very similar solution. There we finally get the black, but now we also have this odd yellow color. There we're almost very close. But as you can see, there's the first iteration, or the first complete k-means, where we actually get all the primary colors from that flag. And here we're quite badly off. I built this into a flipbook, so it's iterating through 20 different k-means solutions just to show it off. So as you can see, we kind of have a couple of problems here, is that we're not extracting the expected 5 colors that we wanted, but then also we kind of still need to tell k-means the number of colors we need to extract. So at least for the second problem, we can use something like the silhouette method, or elbow method to derive that. But our biggest problem is actually that the initial points that k-means is working from is actually probably affecting us, and that those centroids could be converging onto these outlier points that we have, or these pixels that we have within our image. So how are we actually going to improve this? So I identified 3 areas that I would actually improve to get to a workable solution. The first was ridding ourselves of the JPEG red and just going for PNG straight. The second was upping the iteration count on the k-means. And the third was to actually stack multiple k-mean runs together and use the aggregate of that to get the specific colors that we want. Because as you saw over those runs, that for the most part, we get our most representative colors within those images. So it turns out not all file formats are equal. And JPEG has quite a bit of compression happening, but not to the visual eye. For most of us, the images would look similar if I had them on screen. But on a pixel level, you definitely have a bit of contamination, so to speak, or compression that's happening. PNG, on the other hand, it's far less of that problem, and it's also seen as a lossless sort of data compression. So if we take that Antigua and Barbuda flag, you'll see that on the JPEG version, if we completely decompose all the pixels, we end up with over 3,000 colors in that image, with a mean of 100 pixels on average per color. And like you can see, the PNG is much better, actually. All right, so that solved the one problem, but is the iteration count actually going to help us? So what if we did 50 iterations? Doesn't do much. What if we did 100? Also really not much. Even 1,000 didn't make a difference. So unfortunately, since a lot of good results exist, or a lot of good cluster solutions exist, it really doesn't help to up your iteration count. I probably wouldn't exceed 50 anyways for this type of problem. All right, and then in terms of stacking k-means, so a lot of people see this as one of the most efficient ways of looking at cluster solutions, is having multiple, comparing them, and aggregating them to some effect. So this is something that does work. I initially tried this on my problem, but when you have to do 30 plus k-means per flag, and you have 250 flags, we end up with a very long runtime for a very simple problem. So this did not end up to actually be a good solution. But on this note, this doesn't mean we should get rid of k-means. A lot of researchers have worked to, for instance, create k-means++, which is a really good alternative to the normal k-means that we can look at. But all right, rethinking the problem, though, is an easy way of doing this. So I actually thought of, why don't we just random sample from the image? The image is, after all, a complete population. Each one of those points are completely as representative of the points of the flag itself. So I'm running a bit out of time, but in short, I was just reading it in, taking 10% of the flag, selecting the RGB, converting it into a data frame, getting the hex colors, and then actually grouping the values, arranging our counts, and generating the plot. And this looks something like this. So representatively, we're getting far better with our colors. Unfortunately, though, I still need to work on our way to get to a cutoff criteria. So I actually opted to have several cutoffs, but the first one was actually just the mutate, where we would take the mean, minus it from the mean, but only 30% of the mean. And the second was actually to create an index based on the value that would occur the most. Then from there on out, I got it to evaluate with a couple of simple rules. Let me just go on. And then here as well, for the second part, we did a similar thing where we were looking at the initial value divided by the sum count, small or equal. And then we actually had 5 simple rules to score each flag. So in terms of the actual results, this is what I ended up with. So I have about 100 photos here where you can see the corresponding flag with its palette. So as you'll see, for the most part, we were actually quite good off. We were getting some really good colors, and we were getting the primary colors within each flag. There's SA on the left, for instance, with all 6 colors nicely extracted. You'll see some of the others as well. We were getting most of the elements. All right, now before you think that you can just randomly sample an image and be done with it, I do want to talk about limitations. So there's a complex image on your left there. And when I was randomly sampling 10% as I did for the other images, I ended up with that whole palette of like whitish yellow colors. Those are actually the most representative colors within that image, but that's not what when we're looking at that image, would say are the most representative colors. It's rather something closer to k-means or what palette R is actually able to create. So in this instance, you actually have a very complex image with a lot of different spaces, and you do actually require a far more sophisticated technique. On this note, though, going forward, we'll likely be looking more at LSTMs and GANs to actually do this type of operation. And a really nice package that I found was called the color mine package. You'll see that we've given it 3 colors on our left that is from the previous image. And we asked it to give us 2 new colors to complement our palette. And it actually gave us the result on the right. And like you can see, it's very simple code to actually get us there. So that is something you can easily do to enhance after you've done some initial sampling and gotten some colors. All right, in terms of the conclusion, so there's often a combination of your code, package code, and thereof. It's always best to start with a package. But I mean, as you'll see in practice, the package will fall short for a variety of reasons. And from there on out, it's actually worthwhile to go under the hood and see what's happening. And I have to say, I've learned the most by doing so. You'll often see that the combination of package code and your own code will get you the furthest. And then what I've also learned is that a good solution can be complex, but a great solution does not necessarily have to be. And a great solution to one problem will rarely be the solution to another. All right, thank you.